So I'm going to give a slightly exotic talk, touch on a number of different subjects. So first I want to start with a word of caution. Whenever your theorists are at work, you should be cautious about what you hear. And by theorists, I'm including numerical simulators, so everyone other than observers. I mean, when you hear observers, you should probably also be cautious, but for different reasons than what I will talk about. So let's start with talking about the very first star. So this is a plot from work with my former student Madar Naoz, back when she was doing cosmology and not exoplanets. So it's showing, these curves show the predicted first redshift of formation in the universe of a halo as a function of the circular velocity of the halo or the mass of the halo. Now, if you go to molecular hydrogen cooling, so it gives you minimum circular velocity, and you get the first star forming at around redshift 65. So that's the first thing, that if you're talking about the real first star in the universe, it's redshift 65 and not redshift 20 or 30, as in most simulations. And this means a very different environment than what people usually call a first star. And for example, redshift 65 compared to redshift 20, all the densities, the mean density, the virial density are all 30 times larger. The CMB is hotter. A lot of the environment is very different. So I'll talk more about the first star in a minute. But while I have this up here, I want to make some other points. So if you talk about atomic cooling, again, because the universe is so large, you find some very rare events in it. So the first atomic cooling halo formed as early as redshift 47. And even if you go by mass, if you go to Milky Way halo mass, 10 to the 12th solar mass, the earliest one in the universe is predicted at around redshift 11. So we're not saying that JWST in every small field will find a Milky Way, but we are saying that if you look on the whole sky, if you have a way to search for candidates on the whole sky, you expect 1 or 2 Milky Ways, and certainly many more lower mass halos. So just as a general point, for the observers, be aware that the universe is very big. So if you look on the whole sky, you expect to find some objects that are considered very rare and that you will, for example, you're unlikely to find in simulations. So that's for JWST, but also for the SKA, if you're looking for a very bright galaxy or a very massive quasar. For example, between redshift 6 and 12, the total comoving volume that we observe is equivalent to a box of sides 12 gigaparsec on the side. So there's a lot of comoving volume, and you expect some very rare objects. OK, but let's go back to the very first star. So again, from our paper, this was a spherical collapse calculation for the very first star. So redshift 66 in this case, a halo of 10 to the 5 solar masses, which you expect to host the very first star. So this is the overdensity of the region of the spherical top hat. Of course, in the spherical calculation, it goes to infinity when you collapse, and the extrapolated linear overdensity goes to a finite value. Now, the question is, if you ever wanted to really simulate the very first star, how early would you have to start? So if you go back to recombination, you see that the overdensity is above 10%. So even if you were to start at recombination, you would have nonlinear effects of over 10%, and that's not a small correction by any sense. Certainly not when you're trying to do a precise simulation. So you have to keep going. You go to equality. It's about 6%, still not very strongly linear to good accuracy. And of course, once you get to equality, you're stuck, because before equality, there was very little growth of perturbations. So you can actually go back all the way to redshift 30 million or so. And that's actually when the perturbation first entered the horizon after it left the horizon during inflation. And there still you're at a fraction of a percent of delta. It's not very, very small. And when you hit the horizon, of course, you need GR to do things right. So within a spherical collapse calculation, you can look at what is the effect on the halo formation, and the critical threshold, the linearly extrapolated delta, which tells you when the halo forms, is changed compared to the usual calculation by a few percent. Basically, that's the effect of the radiation density. So this is constantly going on and off. the radiation density, the photons affect the expansion of the universe, the baryons, the fact that they were coupled to the photons and didn't follow the dark matter matters, and give you this change. But if you ever wanted to actually do a real simulation of the first star, you would have to do a very different type of simulation than what people are doing. But the first star is to a large degree an academic exercise, and we're really interested in the second star and so on, because first stars were only very few. So I mean, the second star, of course, per region. But once you form a second star, you open a whole other can of worms. So in addition to the difficult problem of star formation itself, you have feedback from the star, you have supernova formation, feedback, metal mixing, X-ray, binaries, black hole formation, and the resulting various types of feedback. All of this stuff. So if you ask people who work on these subjects at the present universe, I think they would all say that none of these are understood in the present universe. So the idea of trying to predict this type of astrophysics at a new regime where there are essentially no observations is a very nice idea, but I suggest some caution. So any prediction that depends on the details of all of these things, I think should be taken with a big grain of salt. It doesn't mean that we don't know anything, so I think theorists can try to give various plausible scenarios. Even more important is to find generic features, for example, the characteristic patterns over the function of redshift and scale of the 21 centimeter power spectrum. Things like this, you can find various generic features that are common to almost any parameters that you would pick from all of these things. And another important thing is to search for model-independent signatures, so things that can appear in the signal that are very clearly there and easy to interpret without all of the parameter fitting, and these kind of signatures, if observed, will let us know, will be more convincing that we know what we're doing. But for the observers, I would suggest that you should take the theorists, as plausible scenarios, as a guide, but you should expect and hope, of course, to find surprises. And maybe the nicest surprise that the JWST would be able to give us would be to see essentially nothing. So I'm sure Roger would agree that this would be the fantastic of the JWST saw nothing, because then it might be a clue to some of these exotic things like fuzzy dark matter. So this paper from 2000 has been mentioned. I guess Tom is here. Jerry maybe is touring Paris. So in this paper, we suggested this number of 10 to the minus 22 electron volt. The idea is that with that mass, quantum effects give you suppression of low mass, of small scale power and halo structure in small halos. Now, the history of this is interesting. So a year after this, I wrote a paper with Zoltan and Jerry, who were in the conference. And this was, I don't know if the first, but certainly one of the first papers to make this detailed connection from, so here we focus on warm dark matter, but from models that try to do something with small scale structure at the present, connecting them to small galaxies at high redshift, so constrained from reionization and also from the need to form the massive black holes that are seen at high redshift. Now, in 2003, WMAP came out with the year one data. They said, of course, that tau is 0.17. Reionization was extremely early. So they actually cited our paper and said, therefore, warm dark matter is ruled out. They didn't even think that we deserved a mention of the fuzzy dark matter. But, of course, fuzzy dark matter was also ruled out in all such models. But then, of course, this high tau went away. So you can see that as a successful prediction if you want. But so it's interesting in that context to look at our paper, how many citations we've had per year. So you can see it started going up, but then after WMAP, it went down and was kind of at a low level. Now, I'm not sure what happened in 2010, but the rest of this looks like this. So I can't resist the temptation to extrapolate. And I think it's interesting that out of 275 citations, only 3 involve any of the authors. So none of us have actually looked at this since. But unfortunately, they don't They don't give Nobel Prizes by citation. So before we all get too excited, I did, when I was preparing this talk, I did a simple estimate. So if you look at warm dark matter, the most stringent limits are considered to come from the lamina of a forest. So here's a paper that involves a number of people in this room. So they looked at the lamina of flux power spectrum from 25 spectra of redshift above 4 quasars. Their conclusion was that there is no suppression of the linear power spectrum at quite small scales, and therefore that for warm dark matter, a 2 keV particle is ruled out very strongly at 4 sigma. Now, I took from the 2 papers that I just showed you, my old papers on fuzzy dark matter and warm dark matter. We give the simple scalings in the 2 cases. So from the comparison, I find that 2 keV for warm dark matter is equivalent in terms of suppressing the power spectrum to a fuzzy dark matter mass of about 7 times 10 to the minus 22. Now, for this model, you really want 10 to the minus 22. Once you get to 10 to the minus 21, all the fuzzy effects are pushed to small scales, and they start to become pretty weak. So I don't know what to do with it. Maybe someone has an objection to this method, but it seems to be basically that this method, if it rules out interesting models of warm dark matter, then it pretty much rules out interesting models of fuzzy dark matter as well. No, but this has an effect on the linear power spectrum as well. Yeah, I'm talking only on the linear power spectrum. The effect on the collapse halos and nonlinear effects are separate. But this, when you calculate, the evolution of density fluctuations with this, it affects the linear power spectrum. That's the only thing I'm including here.
They had a paper yesterday in the archive that went up. They had a paper yesterday in the archive.
Yeah, I know. Now they're claiming even more. That's right, or even 4K kV. So even more strange. No, this is just for the linear power spectrum. The warm dark matter, it was a paper with you, so we took it from equality, but because that's where most of the effect is. And for fuzzy dark matter, I think it's integrated to redshift 0. But in any case, I mean, for warm dark matter, certainly it doesn't change much with redshift anyway, the linear power spectrum. So the what? Oh, in that sense, for the forest. Okay, yeah. Okay, that's a good question. Yeah, I'll check if that makes it. The question is at which redshift did I take the linear power spectrum? So I don't think I took it specifically to redshift 4, and that may make some difference for the fuzzy dark matter. So yeah, good point. I'll check that. So sorry, I did this last night, so it's not. It's only an estimate. I doubt that it has a huge effect. Because no, I think it shouldn't have a big effect. The point of this. I mean, actually, the fuzzy dark matter gives a very sharp cutoff in the power spectrum because I think the scale changes very, very weakly with scale factor, something like power quarter or something, right? So I think, actually, it's probably not enough to save you. It would be like a factor of 1.5 or something. So, okay. I mean, if it's marginal, it might be, but I don't think this is marginal. It's certainly not if the limits from the forest are getting better and better. It's not a marginal. It just wipes out all of these models.
You're actually using a realistic calculation of the linear
part? Yeah, we did it in our paper with Boltzmann equation. I mean, yeah.
In the original paper?
In the original paper, we did that, the linear calculation, yeah.
But the mass does not have to be 7 10 to the minus 22, so you can put some limit on the mass.
Yeah, no, but you want it to be 10 to the minus 22. You want it to be much smaller to have a big effect on galaxies and everything that Tom talked about. If you push it to higher particle masses, then all the astrophysical effects basically go away. They're on scales that are too small.
If you use the Lyman alpha restrictions to
Yeah.
the limit, does that rule out all of them?
No, it rules out interesting models. It doesn't rule out all models. Like Paul said, you can take this mass to be much higher, but just uninteresting in terms of astrophysics, in terms of what we're talking about.
Yeah, except that it could be the dark matter.
It could be true, but it's not. No, sure. That's it, but that's a separate issue.
It could be called dark matter, right? Whereas warm dark matter, you don't get that choice.
No,
You rule
fine.
it out, you rule it out.
Okay.
Don't say rule out fuzzy dark matter. You're just making it fuzzy on the
No, why you say, I mean, for the word dark matter, you can go from 4 keV to 10 to 100, and you can also go to uninteresting masses. Anyway, so let me go on because Paul is next. So Paul made the point, another point related to this yesterday, that you have to be careful with photoheating feedback, which is due to heating of reionization, which also cuts out large or halos up to about 10 to the 9 solar masses. So just the fact that you may find the faint galaxies dropping out, won't allow you to immediately jump up and down and say we've discovered new properties of dark matter. So on the subject of photoheating feedback, I want to say that the idea that we know what this feedback will do to galaxy formation is, again, one of these things where you should be very cautious about. In principle, it's a very simple effect on gas infall. But what about the gas that is already in galaxies when a region gets reionized? So the gas inside galaxies, it can be very dense. You can have self-shielding. You can have mergers that will trigger star formation or black hole activity, even without new infall. So all of that astrophysics is very, very uncertain. So I want to briefly mention a paper with Avi Loeb from 2000, where we presented a plausible model where the fact that you have photoheating feedback may mean that you can have a recovery if you go to higher redshift before this feedback, before most of reionization. So this is the star formation, the cosmic history of star formation rate versus redshift. So if you go beyond reionization, you may expect a bump in the star formation rate. However, even in our paper, we showed that from JWST, you will only see a very small portion of this bump because most of it happened in very tiny galaxies. However, there may be other ways from reionization and other ways to find out whether the star formation rate really went up early or not. And if we're speaking about reionization, so the next thing I want to talk about is what was known in 2004 and also in 21st century cosmology. Well, in 2004, they were basically the same subject because reionization was considered to be the only source of 21st century fluctuations other than primordial fluctuations. Now, there was this model, simulation by Nick Nedin, where so at this point, in 2004, it was unclear what would be the sizes of the H2 regions. So Nick Nedin showed it here in the form of a co-moving mean free path of photons, but it's basically the typical size of H2 bubbles in his simulation. So you see that it's about 1/10 of a megaparsec throughout reionization, and it jumps up only at the very, very end. However, so this was a very small box. People started running larger boxes. Fralnetto et al. Found a few megaparsec bubbles. But there was also the second issue of the topology of reionization. So a number of people have said and have mentioned that reionization occurs inside out, but this was not at all obvious in the early days. So there was this paper that said that reionization should occur outside in, starting in the voids and then going to the overdense regions. There was this simulation by Ciardi et al., the first simulation on 30 megaparsec boxes, and the first one that looked actually on this scale at the typical region compared to an overdense region. And they found significant fluctuations in reionization, but they actually also supported outside-in reionization. They claimed that the protocluster, the dense region, reionizes later. So Avi Loeb and I helped resolve much of this confusion with a very simple but powerful idea, which is that early galaxies were very strongly clustered or biased. So the basic idea is that you have random density fluctuations which need to reach a critical threshold in order to form galaxies. And then if you consider large-scale modes where you have an overdensity, the small-scale fluctuations don't have far to go, so you get lots of galaxies on the large region. If you have a void, you have an empty region of galaxies. And at high redshift, when all the halos are very rare, all these effects become very strong. So small changes in density cause large changes in density of galaxies. So we said that as a result, you expect large regions to achieve reionization earlier than other regions. And we had this plot as a function of the size of the region or the box size of a simulation. And we said that if you look at 10 megaparsec regions, you get a typical scatter in redshift, for example, of when reionization occurs, of 1. So that's a large scatter, which means that you're not seeing a representative volume. for the structure of reionization, you have to go to 100 megaparsec box where delta Z goes down to 0.1, and then you're getting closer. And we noted that reionization should be inside out. Overdense regions should have a much higher enhancement of the number of ionizing sources than the enhancement in such regions of the number of atoms that you need to reionize. Now, this was verified first with a very nice model by Fralnetto et al. That showed in detail the expected sizes of H2 regions. And then people started running very large simulation boxes. So the first one was Ilyev and Paul and Gerald, who are here. And they found these very large ionized regions and very large neutral regions. Okay, now beyond reionization to cosmic dawn, well, basically the starting point of this was Madao et al. 97, which first showed that there are two other cosmic events, basically, that you can see with 21 centimeters. So the Lyman alpha, the rise of the Lyman alpha intensity from stars gives you 21 centimeter coupling through the so-called Waldheisen field effect. And then you have cosmic heating, probably from X-rays. Now, they assumed, and people continued to assume, that these radiation fields were highly uniform. But Avi Loeb and I applied the same idea of strong bias at high redshift to show that actually you get significant Lyman alpha fluctuations. So today, these are considered to be the most promising method probably to probe galaxies out to these very high redshifts. Pritchard and Fralnetto then applied a similar idea to X-ray heating and therefore to temperature fluctuations, and again showed that you get large 21 centimeter fluctuations. And we're all keeping our fingers crossed that the SKA will hopefully detect a combination of all of these sources. So briefly, I want to end with an example of a model-independent signature that we're trying to look for in 21 centimeter fluctuations. So it has to do with these redshift space distortions, which Gerald gave a very nice talk on yesterday. So it basically says that the power spectrum, the 21 centimeter power spectrum, is not isotropic. You expect an anisotropy as a function of the angle to the line of sight. So with Avi, we first showed that this anisotropy allows you to get a lot more information than just from the spherical power spectrum. You get the spherical piece from all the 21 centimeter sources. You get mu to the fourth term, which in principle allows you to learn about basic physics or cosmology. It's just a primordial density power spectrum. And you get a cross term, which gives you the cross correlation between all of the astrophysical sources and the density. Now, as Gerald mentioned, people ran simulations of the EOR. So this was all in linear theory. The simulation showed that with nonlinearities, getting out this physics term is hard. It gets contaminated because it's actually the smallest of the terms. However, the mu squared term is not so small. And it survives nonlinearities much better. So this is from our recent paper. So with Anastasia and with my student Aviad, who is also here. So briefly, what we have here is the mu squared term of the power spectrum as a function of 1 plus redshift, or up here is observed frequency. So this is for a particular model at a particular wave number. At each wave number, you would have this kind of plot versus redshift. So I'm showing the measured p mu squared from our semi-numerical simulations, like in a Mach measurement, compared to the prediction from the simple linear separation. So they agree very well. You get pretty nice separation for the mu squared term. And the point is that this acts as a cosmic clock. It basically tracks very nicely the change of cosmic eras. So you would also see the corresponding changes in the shape of the regular power spectrum. But the mu squared term is nice because it has a sign. It actually goes from positive sometimes where the solid curves, and negative is the dashed or dotted. This is the log plot. So during the EOR, so Gerald mentioned that the mu squared term should be negative. And this is a direct indication of the inside-out nature of reionization, which I talked about, because, again, this is the correlation with density. So anti-correlation is exactly that high-density regions reionize first and give you less 21 centimeters emission. But other eras in cosmic history, during Lyman alpha, this is positive. During X-ray heating, it goes from negative to positive when the universe heats above the CMB for the first time. So a lot of very nice information. Of course, it's a little bit weaker than the spherical power spectrum, so it'll be a little hard to measure. But hopefully, in some of these peaks, you can measure this and see if it's positive or negative. So to summarize, I would caution you to not believe theorists and simulators in great detail. Even the very first star, I mean, it's a problem that you may have heard as being a very clean and simple problem is really not so easy. And once you get to the second star, it's completely, things, you get a lot of other problems. I would urge you to remember that on the sky, you expect very rare objects that you may not find in theoretical papers. For fuzzy CDM, well, it's generated many citations from me, but it may be already killed by Lyman alpha, by Lyman forest. We should check that more carefully. Photoeating feedback is an interesting effect, which suggests that there may have been a recovery of the star formation rate prior to the end of reionization, so watch out for that. The simple idea of strong clustering or bias at high redshift is the fundamental idea that leads to many of the basic predictions of large H2 regions, of inside-out reionization, and of large 21 centimeter fluctuations from both Lyman alpha coupling and X-ray heating. And finally, model-independent signatures. So I didn't talk about this, but I'll just mention the streaming velocity, the relative baryon and dark matter velocity that others mentioned yesterday. So if this is ever important, it comes with a very nice, very clear BAO signature. And I did talk about the other model-independent method, the cosmic clock, which you can do with power spectrum anisotropy. So thank you.
Rennan, before you rule out your own model too hastily, the cutoff in the case of wave dark matter is sharper than for warm dark matter. So,
actually, for both from the linear spectrum, they're both very sharp. I don't think that's a big difference, actually.
Right, but I think there is going to be, of course, additional variance from astrophysics on those scales, related to.
Yeah, so that's a question. So I see there's some papers. I mean, so if you can challenge that method, that maybe there's some remnants of heating fluctuations from different reionization, some other effects on the Lyman alpha forest. I mean, I'm sure not all of the effects have been completely explored. So probably Martin would say that none of these are important, but there's some room there for arguing with the method.
I think we've seen that there is a large variance on those kind of scales you're talking about.
Yeah, so this is redshift 4. We saw a huge variance at redshift 5.5, and yeah, redshift 4 is later, but not by a huge factor. So there could be still some issues. Yeah, so
you might keep in mind the early formation of the solitons in the massive halos that collapse, because that, as I said, you can speculate could promote the formation of black holes at that time. And lead to an additional extra variance. So I think that's an interesting thought to pursue.
Yeah, okay.
I just have a special request. Can I ask the Lyman forest experts, maybe George or somebody else in the audience, to comment on to what extent the fuzzy dark matter has been killed by the what we know about the Lyman alpha
I mean, the only
forest?
point I'm making is that if warm dark matter is killed, then I think all similar models are probably killed as well. So it's all a question of whether warm dark matter has been really killed.
Has it been killed, George? Or anybody else?
2 kb, yes, or not. The genus basically the genes
Mm-hmm.
since we know that it's low, we can put the limit roughly 2 kb.
So why do you say 4 is not? Because are you including the recent paper? Or?
You can start arguing about 4, but
Okay.
Okay,
It's
thanks.
very clear. Okay.
I thought we just sort of broadened the possible universe by saying if you're going to explain large-scale variations in Lyman alpha opacity by the several effects that were talked about earlier in the week, quasars or temperature fluctuations from homogeneous reionization, that this will impact the Lyman alpha forest fluctuations. So
Yeah, so that's a good
we
question.
just forgot that. And now we're quoting them as well, if you're making fluctuations, you're making fluctuations. And you can't throw them away when you do this analysis.
Yeah, I mean, there's two questions. There's a question of scales, that you're talking about large scales, and here's the small scale power spectrum. The other question is Redshift 4 compared to Redshift 5.5. But yeah,
The thing with the standard model of the data is amazingly good. So now you want to add some random iteration, and you say, well,
Not random. No. I just want to.
There's no
I want to go
rule.
back to
There's no rule.
randomization and put in the fluctuations and then inherit those fluctuations over all the scales.
no, I mean, he's saying that the standard treatment that you're using in Redshift 4 doesn't explain the observation in Redshift 5.5. So that's the only room for caution there. I mean, maybe it's irrelevant, but yeah, I mean, it might be irrelevant, but it just said that there's something missing. Okay.